Right, guys, there's a little prelude to the problems 12 to 18. I believe we must use the result of problem 11, which means that we'll have to map the fundamental domain, and that means in particular that we should be able to find the image of the lines and the circles using different matrices in gamma. It says in the book that gamma maps lines and circles to lines and circles, but I would like to have more specific knowledge. What stopped me previously was that operating in general is intractable. So what could one possibly do? Then it occurred to me that gamma is generated, let's just write generated, by T and S. So the problem is much more simple than I originally thought. We just need to find out what T and S does. And T is a translation, 1 unit. So that's simple, it's geometrically simple. S, however, what does that do? And first I took a vertical line and checked what it did. And I have that in this Maple script. I did it by hand first. But for you, I have made Maple do it. So we take a vertical line and maps it by S, and then we have to find A minus A divided by this, point T divided by this. What figure does that make? And it's easy to see that it's a circle, actually with radius 1 divided by 2a and center minus 1 divided by 2a. So that means it's a circle with rational center, so it has center in a cusp, and then it goes through naught, and that's of course the point at infinity, which maps to naught. That's what S does. That means that we get circles, all circles through with rational radii and centers on in rational points going through naught, and then T can give them any translation. So this way we get all the circles with rational centers and rational radii. Or do you say radii? The next question is how does it map a circle? And I started with one of these circles, and I was able to do that by hand as well. And I have actually shown exactly the way I did it. This is not quite clear, is it? Well, S maps to minus x divided by this, and y to and plus I times y divided by this. So that's u and v. And next we recognize that from this we get x squared and y squared, and it occurs in the denominators as well. So we can actually introduce it as variable and then eliminate it. That gives first order equations, so we can find x and y. Actually, the way I did it by hand was using this guy to convert this to x, and then solving for x, and then y is easy. And then I inserted this in the equation and found the equation for the image. And I found out that it mapped to a circle with this center, which is rational, and this radius. Of course, that's necessary. This isn't naught, but we already have covered that because that was circles going through naught in the complex plane, and they are, of course, mapped back to a vertical line by S. So there's no need to think more about that. And then the Mabel way, I write up the equations and then eliminate x and y. Mabel can do that. And then we get this guy, and I take it, yeah. And then I should actually just operate on it to write it in the same way as above. I haven't done that. Never mind. Well, I've done it up here, so there's no point in doing that again. And that means that we still have centers on the real axis at rational points, so it's at cusps, and rational radii. And that's all we need, basically. I wanted to do it in general, so I did the same with an arbitrary circle, and this is what the elimination gave. I believe this is the result when we get a vertical line, and I don't know what the point is of this, but this turns out to be the circle we are looking for. So a circle with arbitrary center actually gives another circle with arbitrary center, and if the radius is rational, then this is a rational radius as well. And finally, the map of a non-vertical line was quite easy. We did the same thing and found a center. If A and B are rational, then the center is a rational point, not on the real axis, but the radius of the circle does not often come out rational. The short story is that vertical lines and circles with rational centers on the real axis and rational radii map to each other by gamma, because they do by T and S. So how do we actually find the results? If we take one matrix in gamma. It has determinant 1. How does it map F here? And first, infinity is mapped to unity. And then how about minus 1/2? That's minus 1/2 plus 5 divided by minus 1/2 plus 6. So that's 9 divided by 11. And that means that this line maps to a circle going through these 2 points. Therefore, it must have center in between, and this is the circle. So not much computation is needed, and we can do the same with 1. Or 1/2, I mean. It maps to 11/13. I believe that's larger, 121, and that's probably 117. This means this one is larger, yes. And then the circle here, how does that map? So we have to find out unity maps to 1 plus 5 divided by 1 plus 7. That's 6, that's 3/4. Just like here. And minus 1 maps to 4/6. That's 2/3. Oops. Three-fourth. If we say this is 3/4 and this is 2/3, we are not quite to scale, then this would be 1/2. So we need to move north a bit. So this way we get this circle. And now we see that I've made a mistake. This line crosses this circle, so this circle should cross this circle. So I've made some silly mistake. I'll just make a break and find it. I just found a few mistakes here. It was 6, so that is 4/5. And 6/7 is larger than these two guys, so this is how it goes. And that means that we have it should combine these 2 points. So it goes here and vertically down there. And then this guy and this guy. And that means that this is the mapping of F. That's my method. Hello, 18th of September 2023. There's really not much to say to problem 10 because we have already done the necessary work in problems, was it 8 and 9? Yes. We found the matrix alpha to be this, so that gamma naught 4 is, well, should we say equal to alpha gamma 2 alpha to minus first. So the fundamental domain of this guy is simply alpha working on the fundamental domain of gamma itself, and alpha works on set, simply putting it to set halves. So all we need to do is to take the domain of the fundamental domain of gamma 2 and then shrink it by a factor 2. In 2021, in the spring, when I worked with these problems, I actually did draw them. Here we have the fundamental domain of gamma itself, and I like to use S of F, and we can just look at how S maps. I infinity maps to naught, omega to this point, so that means this guy is mapped to this circle. And minus 1/2 maps to 2, so it's the unit circle, part of the unit circle. And this one will simultaneously map to this circle. And this circle, it's part of the unit circle with center at naught. So it maps simply changing the direction. So there we have it. Now gamma of 2, we have in the book, so I just divided all the points with 2, so this is the fundamental domain. I'll just show you the code I used for it. I'll just show the code used for F. So it's in LaTeX. And I make a figure with a caption, fundamental domains. I don't think this is necessary, I think that's default. And then I make some lines and some text. It's the points we have here. And then the vertical line, the 2 vertical lines of F, and then the arc. So I put on the center and the radius and the degrees from 60 degrees to 120. As you see, it's all very civilized and easy. And then the definition of F itself. So there we go. That's the That's the guy here. So I find this, though it takes a little while, it's an easy way to draw it, and I always have it at the computer sized any way I want, and I can work with it easy. Well, that's all I had to problem 10 for you.